Hi everyone, and welcome to the second part of our video for section 5.2. This one is going to cover harmonic motion and graphing sums of functions. So our skill objectives for this one are solve harmonic motion problems. Number 2, graph sums of functions. And the conceptual objective is to visualize harmonic motion as a sinusoidal function. Let's start out by looking at the graphs of the sums of functions. And this is really going to be done by the addition of the ordinates, which is the y values. So the first thing you're going to do when you're going to graph something that is equal to like y equals f of x plus g of x, so I want you to graph f of x, I want you to graph g of x, and then take a look at those y values and add them to get me a graph of the sum of the two functions. Let's take a look at this problem we have. It's y equals x minus 2 cosine of pi x. And I want to think of that as x plus a negative 2 cosine of pi x. And when we do these things, you're going to see an interval here. In this case, we're going to look at the interval from 0 to 4. Now, right here in the red, you see the graph of the x, y equals x. So if you notice on there, yes, it's that's 1, there's 2, 3, and 4, and our units are a little bit smaller there. That's why it doesn't look as like the 45-degree angle, but that's what you have there. And in blue, when we analyze that one, we have negative 2 cosine of pi x. Our amplitude is 2. The period is going to be 2 as well. And I know because it's negative here that cosine is going to start at a low spot, so it's going to be at negative 2. And the period is at 2, so it's going to that first period is going to start at 0 and it's going to end at 2. And so if I go halfway, if I go to 1/4 of the way to 2, which will be at 1/2, I'll be on the axis. Then at 1, I'll be above. At 1.5, I'll be halfway between on the axis, and at 2, I'll be down below. And I have to continue that pattern for a second period. Now what I need to do is kind of look at the graphs and estimate where points are going to be in terms of adding the two together. Now the one thing I do know in this case is that at 0, when I add the two together, we have the original at x is at 0, and then our cosine curve is at negative 2. So when I add the y coordinates there, I'm going to get negative 2. So I'm going to do this new curve in yellow, and it's going to have that point right there. In addition to that, I know that it is going to, when the blue function is 0, it's going to be actually hit the y equals x. So I know at 1/2 we're going to be at the same spot as y equals x. So this curve is going to go through that point right there. And now at 1. At 1, we know we're going to be at a high point because when we add these together, that's 1 and that's 2. So at 1, we're going to be up at 3. And I know that is going to be a high point. Okay, because of the fact that it's going to, my cosine function is actually going to start coming down after that. Then another spot that we know, we're at 0 at 1.5. And so I know the curve is going to actually it's going to be the same value as y equals x at 1.5. And now at 2. At 2, we're at negative 2, and it's positive 2, so it's actually going to be 0. And it's going to, at that point, it's going to start going up again. So I have that point. At 2.5, it is going to be on our curve, on the line y equals x, so I'll be up at that point there. At 3, we'll be at another high point. Now that's 2, that's 3, so this is going to go up to 5. And so I count that up, 1, 2, 3, 4, 5. So at there, it's going to come up to this point, and again, we'll be at a high point. And then when we get to 3.5, we'll be back at 0. So it'll be touching again right there. And then at 4, it's going to come down, and it will be at 2. So graphically, what I can see on this is it's going to come down like this. It's going to curve and come like this here, come up. And what we see there in yellow would be the graph of the sum of those two functions. And you can then, now this is going to be an approximation because we can't necessarily go exactly with them, but you can get a good idea of what that graph is going to look like, and then you can double check it by graphing this on your calculator. Additionally, keep in mind that the functions that we add together could be, in this case I had a polynomial line and a trig function, but it could be two trig functions. They may or may not have the same period. They could be two trig functions with different periods as well. Just remember to graph the two functions over the interval that you're going to be given. So in each problem like this, you will be given an interval that you know you're going to work from. So you're going to want to graph it over that interval, and once you have that, give me your best estimate in terms of where those points are going to be located. Again, notice the points I found. I located where the functions were equal to 0 in each case, and use that because then I know that it's just going to be on the graph of the other function. And I also used the high or low points that we had as well. So that's really in a nutshell, what you're going to want to do when you're asked to graph two of these functions like this. Next, let's take a look at the different types of motion, harmonic motion. The first type we have is what's called simple harmonic motion. And this is where we have an unvarying motion. In other words, this thing is not going to stop. It is just going to keep going back and forth, back and forth. It's something where it's just bouncing up, down, up, down, up, down. There's a couple ways this can happen. One is that we live in fantasy land and we don't have any resistive forces like friction. Friction out there right now is a resistive force. We can't just go and push something and it goes on forever. It's going to stop because of friction. Or the other option is that the energy that's being supplied to the object to keep it in motion exactly overcomes the resistive force. It's got to be that it exactly overcomes. That's so that it doesn't change. When you have the simple harmonic motion, the amplitude and the period remain constant. Okay, so there won't be any change with that. Now we do have some ways of modeling simple harmonic motion. We use, because of the fact that it is just going up and down, there is no change in the amplitude. It is very sinusoidal in how it looks. The position of an oscillating function around equilibrium position at time t is modeled by y equals a sine of omega times t, or y equals a cosine of omega times t. Remember that omega in this case is the angular frequency, absolute value of a is the amplitude, and the period is going to be 2 pi over omega, and omega must be a positive number. Now when we talk about the equilibrium position, what that means is that the energy being supplied is exactly equal to any resistive forces that are out there. So that's what's happening when we have that equilibrium position. Let's take a look at an example of a problem that they might ask you to do in terms of simple harmonic motion. What we have is a weight on a spring, okay, and in this case, the model that we have for this situation is going to be y equals a times the cosine of t times the square root of k over m. Now notice that both the k and the m are inside of the square root. The absolute value of a is the amplitude. T equals the time in seconds. M is the mass of the weight, and k is a constant that is related, that is particular to that spring. Okay. Now what we're going to be given is, in this case, we have an equation y equals 4 cosine of 1/5 t times the square root of k. And what they're going to ask us to do is identify the amplitude and the mass of the weight on a spring. Okay, now keep in mind what's happening is that we have a spring attached on top, the weight is on the bottom, and this weight is bouncing. And it is going to continue to bounce up and down, and it's going to be simple harmonic motion, so there is no change in it is going to constantly go up to the same height and go down to the same height. Now, what happens here, when you work on a problem like this one, you've got to get it into the form that they've given you. In this case, this is what we have. So if I'm going to identify the amplitude and particularly the mass, I realize I have to look at underneath the square root. Now also notice there is no number in this formula that they've given us. There's no constant in front of the t. Any constant that is in front of the t must be brought inside the square root so that we can use it to help us identify what the mass is. So on this particular problem, what I have, this 1/5 needs to be brought inside the square root. So what we have there, I have y equals 4 times the cosine of, I'm going to take the t here, and now I'm going to need to rewrite this so that 1/5 can go back inside the square root. And what you have to keep in mind, that 1/5 on the outside would be equal to the square root of 1 over 25 times the square root of k. You got to look at that and recognize that this right here is the same as 1/5. And that by properties of square roots is equal to 4 cosine of t times the square root of k over 25. Now, this particular function is in the form that they gave us in the problem. And so I can now identify the pieces of information I need to find. In this case, the amplitude is going to be 4 centimeters, and the mass is equal to 25 grams. Remember, the value that is up here in this formula, the denominator, where the number underneath the k is the mass. So in this case, the 25 now is underneath that k, so that is the mass of that object, of the weight in grams. The second type of harmonic motion is what we call damped harmonic motion. And the idea behind damped harmonic motion is that the amplitude is going to decrease as the time increases. In other words, think of it this way. You're on a swing, okay? When you're on a swing, if you get it to where you're as high as you want, and then all of a sudden you stop doing anything to put energy in. A lot of times people will call it pumping it. You stop pumping your legs, and you just let the swing go. What's going to happen is that the height that you go is going to start to get lower, but the amount of time it's going to take for you to swing back and forth will remain the same. That is what's called damped harmonic motion. So what happens there is, number one, the resistive forces are there and you can't overcome it, or we stop applying the new energy. And so you see, when you have damped harmonic motion, you see this type of behavior here, and eventually you are going to come to a stop. The third type of harmonic motion that we have here is resonance. And this occurs when you start slow and then the harmonic motion, the oscillations, the amplitudes get higher as time increases. So it starts out low, it's just going to go up and down, and just get higher and higher and higher as you go along. Now this is really going to happen when you are applying energy and you're applying more energy than is necessary to overcome any resistive force. An example of this type of thing would be where if we go back to the swing example, where somebody is on the swing and they are not applying any force, but somebody comes and pushes them. So you push them once, you push them again, and you keep pushing, and then each time they are going higher and higher with each push. So that would be an example of resonance. This now will conclude the video for part 2. I think this is a little bit shorter than the last one. So with that, you do have your graphs that you should be working on to complete from the graphing of the sine and cosine functions that we did in class. And then we'll have some additional problems to work on with this as well. So good luck, and hope everything is going well, and I will see you at our next class.